In this video we are going to continue our study of the motion of a particle in a plane. Now in the previous video we saw that if we know the rule giving the displacement of the particle as a function of time, then we can differentiate that to obtain the velocity of the particle as a function of time. And if we know the velocity as a function of time, then we can differentiate that to obtain the acceleration as a function of time. If on the other hand we know the acceleration as a function of time, the fact that we know that integration undoes the process of differentiation means that if we start with the acceleration as a function of time, we can integrate and obtain the velocity as being the integral of the acceleration. And if we know the velocity as a function of time, then we can integrate that to obtain the displacement as the integral of the velocity. Now, since we differentiate vectors component by component, we're going to do exactly the same when we do the integration. We're going to integrate vectors component by component. And it is important to remember that each time we do an indefinite integral, we need to put a constant of integration into our answer. And then we shall have to use the initial conditions that we are given to find out the value of that constant of integration. So, let's have a look at some examples. So for our first example, we have a particle P of mass 3 kilograms moves in the xy plane so that at time t, where t is greater than or equal to 0, its velocity is v, where v is the vector whose x component is 3t squared minus 6t, and whose y component is 12t plus 8. And the first thing we're being asked to do is determine the velocity of the particle at t equals 1 and t equals 3. Well, that's easy. That's just a question of substituting in. So when t equals 1, the expression for the velocity is v equals 3 times 1 squared take away 6 times 1. So that's negative 3 for the x component, and 12 times 1 plus 8, which is 20 for the y component. So when t equals 1, we've got v equals minus 3, 20. When t equals 3, the velocity is going to be 3 times 3 squared take away 6 times 3, which gives me 9 as the x component, 12 times 3 plus 8, which gives me 44 for the y component. So when t equals 3, we've got the velocity is given by the vector 9, 44. For part B, we've got to determine the acceleration of the particle when t equals 1 and when t equals 3. We know that acceleration is the derivative of the velocity. So we've got the acceleration is the derivative of our vector 3t squared minus 6t, 12t plus 8. And in the previous video we saw that we differentiate vectors component by component. So the derivative of 3t squared minus 6t is 6t minus 6. The derivative of 12t plus 8 is just 12. So the expression for the acceleration is 6t minus 6, 12. So when t equals 1, the acceleration is simply going to be 0, 12. And when t equals 3, the acceleration is going to be 12, 12. For part C, we're given that at t equals 0, the particle is at the point 0, 4. Determine the position of the particle at time t. So, we want the displacement of the particle away from the origin at time t. Now, to get the displacement from the velocity, we know that displacement is given by the integral of the velocity. So in this case, we've got to integrate the vector 3t squared minus 6t, 12t plus 8. We integrate vectors component by component. The integral of 3t squared minus 6t is t cubed minus 3t squared plus a constant. And I'll put the constant as being alpha. The integral of 12t plus 8 is 6t squared plus 8t plus a constant, which we'll have as beta in this case. Now, we've got to use the initial conditions to find the values of alpha and beta. So we know that when t equals 0, the particle is at the point 0, 4. In other words, when t equals 0, the vector 0, 4 is the displacement, but when we substitute t equals 0 into our expression for r, we get 0 cubed minus 3 times 0 squared plus alpha as the x component. In other words, the x component is alpha. 6 times 0 squared plus 8 times 0 plus beta. In other words, just beta for the y component of r. So we know that 0, 4 has got to be the value of the vector alpha, beta. In other words, alpha must equal 0 and beta must equal 4. So that now tells me that the expression for the displacement is t cubed minus 3t squared plus nothing, 6t squared plus 8t plus 4. If that's the displacement of the particle at time t away from the origin, it means that the position of the particle at time t is the point t cubed minus 3t squared, 6t squared plus 8t plus 4. Moving on to part D, we have to find the resultant force acting on the particle when t equals 3. And that's nice and easy because it's simply an application of Newton's second law. Newton's second law tells us that the resultant force acting on a particle is the mass times the acceleration of the particle. Now when t equals 3, we know that the acceleration is 12, 12. So the resultant force that we've got is 3 times the vector 12, 12. In other words, the vector 36, 36. And the units presumably are in newtons. For part E, we've got to find the speed of the particle at the instant when it's at the point 50, 194. So if the particle is at the point 50, 194, then we know the displacement is 50, 194. In other words, the value of t cubed minus 3t squared, which is the x component of the displacement, must be equal to 50. And the value of 6t squared plus 8t plus 4, which is the y component of the displacement, must be 194. So we've got the quadratic equation, which is the easier one to work with, is 6t squared plus 8t plus 4 equals 194, or 6t squared plus 8t minus 190 equals 0, which gives me either t equals 5 or t equals minus 6 1/3. Well, we know we're only dealing with positive times, so we must have t equals 5. And it's worth just checking at this stage that if we've got t equals 5, then t cubed is 125, take away 3t squared is take away 75, which does indeed give me 50. So when t equals 5, then the velocity of the particle is given by 3 times 5 squared, take away 6 times 5, which is 45 as its x component, 12 times 5 plus 8, which is 68 as its y component. The speed of the particle at this instant is the square root of 45 squared plus 68 squared, which is the square root of 6,649, in other words, approximately 81.5 meters per second. For our second example, we've got a particle that's moving in the xy plane in such a way that it starts at the point 5,2 with initial velocity 1 minus 2 meters per second, and at time t, where t is greater than or equal to 0, it experiences an acceleration of 8e to the minus 2t minus 2e to the minus t meters per second squared. We've got to find the velocity and the position of the particle at time t and describe the motion of the particle as t tends to infinity. Now, we know then the acceleration is the vector 8e to the minus 2t minus 2e to the minus t. We know we can obtain the velocity by integrating the acceleration. So we've got the velocity is the integral of 8e to the minus 2t minus 2e to the minus t. If we integrate 8e to the minus 2t, we obtain minus 4e to the minus 2t plus a constant alpha. If we integrate minus 2e to the minus t, we obtain 2e to the minus t plus a constant which we'll call beta. When t equaled 0, we were told that the velocity was 1 minus 2. So, putting t equals 0, we've got a velocity of 1, velocity equaling 1 minus 2. But our formula for the velocity says that the velocity should be minus 4e to the minus 2t plus alpha, 2e to the minus t plus beta. So putting t equals 0 into that, we get the velocity taking the form minus 4 plus alpha, 2 plus beta. So the fact that we know the velocity has got to be 1 minus 2 tells me that I've got 1 must equal minus 4 plus alpha. In other words, alpha must be 5. And I've got minus 2 equals 2 plus beta, which means that beta must be minus 4. So I now know that the velocity is given by the vector 5 minus 4e to the minus 2t and 2e to the minus t take away 4. We know that we can obtain the displacement by integrating the velocity. So, integrating the velocity means that I've got to integrate 5 minus 4e to the minus 2t and also integrate 2e to the minus t take away 4. The integral of 5 minus 4e to the minus 2t is going to be 5t plus 2e to the minus 2t plus a constant. I've used the letter gamma for the constant. The integral of 2e to the minus t take away 4 is minus 2e to the minus t minus 4t plus a constant which we've written as delta. To find the values of gamma and delta, again I must go back to the initial conditions, and we've been told that the particle starts at the point 5,2. So when t equals 0, the displacement is the vector 5,2. On the other hand, when t equals 0, our rule for the displacement gives 0 plus 2 plus gamma as the x component, and minus 2 minus 0 plus delta for the y component. So we've got 5 must equal 0 plus 2 plus gamma, which means that gamma must equal 3. And we've got 2 must equal minus 2 minus 0 plus delta, which gives me delta must be equal to 4. So we've now got our displacement at time t is given by 5t plus 2e to the minus 2t plus 3, 4 minus 2e to the minus t minus 4t. So that at time t then, the position of the particle is the point 5t plus 2e to the minus 2t plus 3 as the x-coordinate, and 4 minus 2e to the minus t minus 4t as the y-coordinate. Now finally, we've got to consider what happens to the motion of the particle as t tends to infinity. And the important thing to notice is that as t tends to infinity, e to the minus 2t tends to 0, and e to the minus t tends to 0. So, as t tends to infinity, the first thing we notice is that the velocity is getting closer and closer to a constant value of 5 minus 4. And if we look at the displacement equation that we've got, we can see that r is getting closer and closer to an expression of the form 5t plus 3, 4 minus 4t. So, the point that the particle's at is getting closer to having an x-coordinate of 5t plus 3 and a y-coordinate of 4 minus 4t. And if we eliminate t from those two expressions, well, if we eliminate t from the x expression, we get t equals x minus 3 divided by 5. Substitute that into the y expression. I've got y equals 4 minus 4 lots of x minus 3 over 5. We can multiply that up by 5 to clear the fractions, so we've got 5y equals 20 minus 4 lots of x minus 3. In other words, we've got 5y plus 4x equals 32. So for large values of t, the motion of the particle is very close to the line 5y plus 4x equals 32. And what's more, because the velocity is constant, we can say that it's moving along this line 5y plus 4x equals 32 with a speed very close to root 41 meters per second. Finally then, we've got a question here where the question's set up in terms of the vectors I and j, and remember that I and j are just the vectors 1, 0 and 0, 1. And we've got a little question there for you to do. We're told the acceleration, we've got to find the velocity and displacement at time t, we've got to find the average velocity over an interval of motion, and we've got to find the times during the motion when the particle is moving parallel to the x-axis. So have a go at that question, take your solutions along to your next lesson, and that's it for this particular video.